So we'll look at our homework from last night, 2, 5 to 8, and 10 to 16, specifically 10, 11, 12, and 15. Number 10 says, list at least two differences and two similarities between gravitational and electric fields, gravitational and magnetic fields, electric fields and magnetic fields. Tell me, I don't care what you give me here, just start listing stuff. Similarity, difference, whatever. Electric field, gravitational field, whatever, it doesn't matter. Just give me something for question A, B, or C. Tell me some similarity or difference.
Both can attract?
They can all attract, actually, right? So that's a similarity between all three of them. Gravitational, electric, and magnetic fields, they can all attract. Good. Yep. They're all vector fields. That's another similarity between all three of them, right? They're all vector fields. Another similarity, another difference, whatever. Got a couple similarities, and it works for all three of them. What about a difference between two of them or between all three of them? Yeah, Bruce? Electricity and magnetism also will deal with repulsion. So we could say between electricity and gravity, they both attract, but only electricity repels. Between electricity between magnetism and gravity, same deal. Okay, both attract, but only magnetism will repel. We could address another similarity there between electricity and magnetism is that we can have both attraction and repulsion for both of them. What about the strength of the fields? We don't really want to compare the strength of a magnetic field with a electric field because a lot of times we consider the electromagnetic force kind of a combined thing, but we can certainly compare both of them to the strength of a gravitational field or force. What's stronger? Electricity, electromagnetic force, electricity, magnetism, or the force of gravity? Yeah, electricity and magnetism are stronger than the gravitational force. So you could say as a difference, the gravitational force is weaker than electric. It's also weaker than the magnetic force. Yeah, I don't know how many we've listed here, but we listed a bunch. That type of thing is what we're looking for. Number 11, he says, using the domain theory, explain the following observations. A magnet attracts an unmagnetized ferromagnetic material. We got a simple, quick, one-sentence answer to this question. How does a magnet attract an unmagnetized ferromagnetic material? Yep, Julia? Yeah, it temporarily aligns the domains in the same direction as the domains of the magnet, right? Stroking a nail with a magnet magnetizes the nail. That's pretty much the same thing, right? It aligns the domains, but if you stroke it, it tends to be a little bit more permanent. Okay, I wouldn't want to say permanent, because that effect will disappear, but it lasts longer than if you just bring it nearby, right? And a metal table leg affects a compass. If I bring a compass near a metal table leg, okay, that table leg will definitely affect the compass. How come? Using the domain theory. Again, it's the exact same thing as, hey, what are you doing to the table leg? What is the compass needle? The compass needle is a mini magnet. So when you bring it nearby the table leg, what happens? It attracts to the non-magnetized ferromagnetic material, right? It's exactly the same as A. It's exactly the same as A. You cause the domains in the table leg to become temporarily aligned in the direction of the compass needle, and therefore the compass needle would be attracted to it. Next question was number 12. Why does dropping or heating a bar magnet decrease the magnetic properties? I know some people have got this because there were some people asking me about this one yesterday, and I helped some people out with it. What do those two things have in common? When a bar magnet hits the ground or when a bar magnet is heated, what do they both have in common? Change in energy. You're adding energy to it, adding kinetic energy to it. When you add kinetic energy to these domains, what happens? Kind of like right now, every single one of you, I think, is facing forward. You're aligned. Okay, you're aligned. You're facing the front of the room. But if all of a sudden we add a bunch of kinetic energy to this room, okay, by cranking the music up or adding some heat to it or something, we add a bunch of kinetic energy to this room, then all of a sudden people start looking in other directions, right? People start aligning themselves in different directions. So what happens here when we drop a bar magnet, it hits the ground, or when we heat a bar magnet, okay, we're adding kinetic energy to the system, and that causes the domains to start pointing in different directions. The kinetic energy does. And finally, number 15, do magnetic field lines always run parallel to the surface of the Earth? Get a good diagram of the Earth right here in number 13, actually. Do magnetic fields always run parallel to the Earth? Well, they're pretty much parallel to the Earth here, right? Here and here. Are they parallel to the Earth here and here? No, not at all. They're almost, in fact, they're closer to being perpendicular to the Earth at the North Pole and the South Pole. And that's why it's difficult to get an accurate reading with a compass needle at the poles. The compass wants to point parallel to the surface of the Earth, right? If I hold the compass like this, parallel to the surface of the Earth, then the needle wants to point parallel. But if it's at one of the poles, the compass needle has to point either downwards towards the Earth or upwards away from the Earth. And a regular compass can't do that. It's all because the field lines are not parallel to the Earth at the poles. Compasses work really well here, not so well here, and not so well here because of the field lines being almost perpendicular.